Thank you to everyone for your time today. My name is Cameron Gottlieb, and I am the North American Business Manager for AGC Plasma Technology Solutions. Today, I will be speaking about recent innovations in the field of ion implantation surface treatments for large area substrates, with a particular focus on its unprecedented scalability for commercial applications. I will first provide some brief background on AGC. Asahi Glass Company, or AGC, is a worldwide materials company based in Tokyo and the world's largest producer of glass. AGC has grown substantially both organically and acquisitionally over the past century with major footprints in Asia, the EU, and the Americas. AGC employs over 50,000 people worldwide across 5 continents. AGC's glass technologies are widely used in many industries. In fact, 1 in 4 cars globally is using AGC automotive windshield glass. Here you can see examples of large area glass products created by AGC. In this case, solar control glass on the famous Renzo Piano designed skyscraper in London, commonly known as the Shard. By precisely controlling the application of thin layers of silver and other materials on the glass, we create energy-efficient functional glass which allows transmission of only the visible light spectrum, while blocking out room heating infrared radiation. Importantly, a keen technical know-how enables AGC to also control the aesthetic properties of the glass for seamless design integration. Glass is no longer just a low-tech building material. Increasingly, glass is an important substrate for a wide range of embedded functionalities to support the technological infrastructure which is demanded by the ascendancy of autonomous driving systems, 5G connectivity, environmental regulations, and, especially during recent times, the need for antiviral surfaces. After the production of glass sheets in the float line, most of the glass we produce is subsequently processed downstream to add various functionalities, like solar control or anti-reflective coatings, for example. This is commonly performed using some form of surface modification, oftentimes with the application of a thin film coating. Central to this effort is the business unit known as AGC Plasma Technology Solutions. AGC Plasma is a group of expert plasma coating scientists and engineers who are responsible for the continuous support of AGC's global coating operations, as well as for the execution of the company's innovation roadmap in collaboration with global R&D teams. We are an equipment manufacturer, but with a unique history and operational experience in the industrial scale-up of dozens of complex coating products. Leveraging this experience, we strive to identify new industrial needs and innovate solutions by surface treatment of not only glass, but also polymer films, textiles, and metal rolls. We develop industrial solutions not only for traditional coating applications, but we also develop alternative surface treatments like ion implantation. Now that you hopefully have a clearer sense of AGC's footprint in the world, let's dive into the specific focus of today's presentation: recent innovations in ion implantation surface treatment for large area substrates and its commercial applications. I will first step through the background and brief history of ion implantation technology. I will then pivot to an overview of anti-reflectivity by ion implantation. Finally, I will discuss the scalability of such processes for commercialization, along with the production equipment platforms we have developed. This will prove an important point as industrial scale production using traditional ion implantation, like with microelectronics for example, can be extremely capital intensive, requiring prohibitively large equipment footprints and complex designs. AGC's ion implantation tools are specifically designed to provide a simplified and versatile process with a small footprint. Ion implantation is a surface modification technology whereby ions of a particular element are produced in an ion source and are electrostatically accelerated to very high energies, often to several hundred keV. The ions are guided to impinge onto the surface of a solid target material, whereupon a collision cascade is caused by the incoming ions. The result is the implantation of ionic species into the crystal structure of the target surface material itself, which can cause a range of chemical and physical property changes. This enables the modification of surface properties without affecting the bulk material. Ion implantation as a surface modification process emerged during the 1970s as a method for doping semiconductors to create charge carriers for p-n junctions. Since that time, numerous applications have emerged for controlling properties like hardness, corrosion resistance, and lubricity. Here we report even manipulation of optoenergetic properties like anti-reflectivity. Unlike additive surface technologies like traditional vacuum coatings, ion implantation does not change the dimensions of the substrate and in fact enables a markedly more robust and abrasion-resistant functional surface. We will next see that there exist even further advantages of ion implantation relative to traditional coatings. As more and more important information is delivered to us through digital displays in the form of mobile phones, smartwatches, traffic information, infotainment systems, and HUDs, the demand for a highly visible screen in dynamic viewing conditions is growing exponentially. Typical anti-reflective coatings are produced by depositing a complex stack of low-index and high-index thin-film materials to create destructive interference patterns. We report here an alternative anti-reflective surface treatment method using ion implantation, which solves some of the disadvantages of traditional interferential coatings. Anti-reflective surfaces can be produced using ion implantation by creating a refractive index gradient from the glass surface down to the maximum ion penetration depth, in this case about 500 nanometers. Multi-charged nitrogen ions can be selectively implanted into the glass surface to various depths in order to create the appropriate index gradient. This ability to precisely manipulate the implantation of multi-charged nitrogen ions into the glass surface creates porosity, or bubbles, which locally affects the refractive index. In this manner, a highly engineered surface treatment can be designed. The maximum reflected light is a function of the current dose, while reflectivity at specific wavelengths can be controlled by the applied voltage. Interferential AR coatings are an excellent solution for many applications, but an ion implantation surface treatment can offer advantages in two important ways. Firstly, AR coatings by ion implantation result in a high degree of angular color stability. You might notice sometimes that when viewing a coated optical surface from various angles, a rainbow effect can be observed. This is typical of traditional interferential coatings and often leads to undesirable cosmetic or functional effects. AR coatings by ion implantation, in contrast, appear the same to the viewer from any viewing angle. Secondly, anti-reflective treatment by ion implantation allows a much more robust and abrasion-resistant solution. This enables applications with rough substrates or those used in environmentally aggressive conditions to be readily used. AR coatings by ion implantation can be optimized for specific spectral ranges like the visible for display applications or in the near infrared, for example for LiDAR applications. The process can be performed on a range of substrate materials like glass, sapphire, and semiconductors. The ion implantation surface modification process developed by AGC Plasma is highly versatile and accommodative to various processes and industrial applications. Our equipment platform enables straightforward manipulation of process parameters to create a customized surface treatment. The process gas can be selected to control the ionic species to be implanted into the substrate. Different ions can impart a range of chemical or physical property changes, depending on the application. For example, stoichiometric or morphological character of the implanted surface can be controlled. By manipulating the applied voltage to the ion source, the ion penetration depth can be controlled, while the treatment concentration can be controlled by the dose of ions. The flexibility enabled by these parameters allows for a wide range of surface property enhancements, like hardness and corrosion resistance. It is important to highlight here that the process is compatible even with flexible and three-dimensional objects. This opens the door to a tremendous number of applications. AGC Plasma is fully capable to support product development and optimization for custom applications. Elon Musk once tweeted, "Production is hard. Prototypes are easy." I think many people here at SBC would agree that this also holds true for plasma coatings. As a company which produces 500 million square feet of glass coatings per year, we at AGC Plasma are intimately aware of the challenges of scaling surface treatment technologies. In fact, it is our core competence to not only design novel surface treatments, but to efficiently scale them in a way that enables their broad adoption in the global supply chain. Ion implantation historically is not a process which is optimally suited for large area applications due to the small size of the ion beams. Here we show a preliminary effort to scale a traditionally limited area surface treatment process to a commercially practical method. The methodology in this case involves the combination of multiple ion sources situated above a moving substrate platform. Here we show the result after process optimization of a highly uniform surface treatment of a large area glass substrate. It can be seen from the reflectivity data of 15 points across the substrate surface that the reflected light percentage is stable across all 15 samples and for the entire measured wavelength spectrum. This implies a repeatable and stable surface treatment process. This is in fact the largest glass form factor ever processed with this treatment. AGC uses a combination of innovative hardware developments and advanced simulation models to optimize process technologies. Operational efficiency, simplicity, and low total cost of ownership are guiding principles for AGC during technology scale-up. A key part of that effort is realized in our own custom-designed ECR ion source. ECR, or electron cyclotron resonance, uses an extremely high-energy plasma excited by 10 GHz microwaves in combination with magnetic fields to create a large number of charged ions. This is a crucial component of our implantation process because it is what serves as the ion source. In anticipation of industrial scale-up, it was foreseen to design our ECR source with a small footprint and minimal parts for a reliable and robust operation. We use only the essential components along with customized modifications which are optimized for this particular process. AGC Plasma commercialized the ion implantation technology for both laboratory scale and, we are quite proud to say, for large area industrial scale. Here you can see the Ion Lab 400 tool for smaller scale development or production. It relies on a moving substrate platform to process substrates up to 400 by 400 millimeters square. An optional lock chamber can be offered for faster throughput. Our industrial coating platform is called Ion Pro 1800 and uses 5 individual ion guns to enhance production throughput, with design capacity for an even higher number of ion gun sources for further throughput. Large area substrates up to 1800 by 1600 square millimeters can be processed with a lock chamber for efficiently coating multiple batches. Substrate platforms control the treatment profile with XY axial motion. This platform represents an exciting engineering achievement as the first and only of its kind to offer large area format ion implantation surface treatment for industrial production at this scale. AGC Plasma Technology Solutions is a world-class leader in advanced surface treatment technologies and industrial process equipment. Our innovations in the field of ion implantation surface treatment will enable an entirely new class of commercial surface technologies, from advanced display glass to state-of-the-art LiDAR systems on the next generation of autonomous vehicle systems. Our proven experience in the large-scale industrialization of novel surface treatment technologies and products is reflected in the Ion Pro platform, the world's largest of its kind. As continuous innovation is crucial to AGC's mission, we already foresee the next stage of industrialization for production beyond the limitations of the Ion Pro 1800. But perhaps this is a topic for next year's TechCon. Finally, I would like to acknowledge the team of AGC Plasma who led this work, in particular Nicolas Revolta, Philippe, and Grazia Laracuta. Additionally, I wish to acknowledge the government of the Belgian Walloon region and the European Union for their support through the Wally Beam project. I would be delighted to respond to any questions or comments during the live Q&A following the conclusion of this presentation. Please do not hesitate to reach out directly at any time after the conference. My contact details are noted here.